Hello, good morning. So, uh, now today in this session we are going to discuss about the inverse Laplace transform of functions. So here, uh, anyway, if we have a function f of t with a Laplace transform, capital F of s, then we say that f of t is the inverse Laplace transform of capital F of s. So we write L inverse of capital F of s is equal to f of t. And uh, there is no simple formula by which we can calculate the inverse Laplace transform of a given function of s. But what we are going to do is we tabulate the Laplace transforms of uh, number of preliminary or elementary functions, and using that function and its Laplace transforms, we are going to calculate the inverse Laplace transform of some common type of expressions. And anyhow, we start with a simple example. Just consider a function 1 by say s square plus 6s plus 18. So this is a simple rational expression, and we are looking for the inverse Laplace transform of this particular expression. And uh, anyhow, so far we don't have any direct function in t for which the Laplace transform is 1 by s square plus 6s plus 18. So for that, our procedure is like this. Uh, we just rewrite it as 1 by s square plus 6s plus 18 is equal to, in the denominator we have a quadratic equation, and we have to rewrite it as a perfect square. For that, it is s square, that is a square plus 2ab plus, if there is a b square, then it becomes f of a square. It is 2ab, 2 into s into something. This we consider the half of coefficient of s, that is 6 by 2, that is 3, half of coefficient of s. Then how will we make it as a perfect square? So the process is like this. Uh, to make it a perfect square, we simplify like this: s square plus 6s plus, we add the square of half of coefficient of s. So 6 by 2 is 3, 3 square is 9, then we minus a 9, then plus 18, and this become 1 by this s square plus 6x plus 9 is s plus 3 the whole square. Then what remains is plus 18. Plus 18 minus 9, that is plus 9. Now, uh, so this is equal to 1 by s plus 3 the whole square plus 3 square. Now, this particular form, if you consider the Laplace transform of say sine 80, it has the Laplace transform a by s square plus a square. So instead of a, we have 3. So here we need a multiplication by 3 and a division by 3. So if we multiply it with 3, and if we divide it by a 3, it becomes something like the inverse Laplace transform of 1 by uh, Laplace transform of sine 80. And if we take the concept of shifting theorem, then you raise the at into f of t as a Laplace transform of s minus a, and that is s is replaced with s minus a. So here, if you observe closely this expression, it is nothing but the Laplace transform of sine 3t, in which s is replaced with s minus minus 3. So it is equal to this 1 by 3 is a constant, since inverse Laplace transform is also um, what we call, it's also a linear operator, and this is the Laplace transform of sine 3t. Then there is a shifting of minus 3, so it is erased minus 3. So this is the Laplace transform of our required function, erased minus 3t into sine 3t divided by 3. So this is how we find the inverse Laplace transform of uh, a function. So we reduce the rational functions into a form which is familiar to us, and then calculate the inverse Laplace transform. So in this particular session, we are going to discuss some methods, some tricks using which we can reduce the given rational functions into a familiar form. So anyway, advise you to uh, have the Laplace transforms of elementary functions for reference. Anyway, let's consider another example. Find the inverse Laplace transform of 3s plus 5 divided by s square plus s minus 6. So this is equal to uh, s square plus s minus 6. Either we can split it into two fractions. There are many different methods. So let us illustrate a new method or a different method to solve this Laplace transform. For that, uh, what we are going to do is 3s plus 5 divided by this s square plus x minus 6 can be factorized as s minus 2 into s plus 3. It's a simple factorization. Then this one can be rewritten as a by uh, s plus 3 into plus b by s minus 2. That is, we are going to use the concept of partial fractions. Then this will give to an implication or an equation like 3s plus 5 is equal to a into s minus 2 plus b into s plus 3. That can be obtained by multiplying everything with the s minus 2 into s plus 3. Now, if we substitute s is equal to some s is equal to 2, this will give, when s is equal to 2, 6 plus 5, that is 11, is equal to, the first time will vanish, second time plus is b into 2 plus 3, that is 5. That gives b equal to 11 by 5. And if we substitute s is equal to minus 3, what we get is minus 3 into 3, that is minus 9 plus 5 minus 4 is equal to, the second time will vanish, so the first time become a into minus 3 minus 2, that is minus 1. That will give a is equal to 4 by 5. So these are the values of a and b. So from here uh, we can express 3s plus 5 divided by s minus 2 into s plus 3 is equal to uh, a by s plus 3. A is 4 by 5. 4 by 5 into 1 by s plus 3 plus b is 11 by 5. 11 by 5 into 1 by s minus 2. And now we can take the inverse Laplace transforms on both sides, and that will give the inverse Laplace transform of 3s plus 5 divided by s minus 2 into s plus 3 is equal to 4 by 5 into inverse Laplace transform of 1 by s plus 3 uh, plus 11 by 5 into the Laplace transform of 1 by s minus 2. Now we have Laplace transform of e raised to at is equal to 1 by s minus a, and using this result we get 4 by 5 into it is the 1 by s plus 3 is the Laplace transform of e raised to minus 3t plus 11 by 5 into the Laplace transform of inverse Laplace transform of 1 by s minus 2 is the e raised to t. So this is our uh, inverse Laplace transform of given function, and the same can be calculated using different methods. We can, okay, I think this is a method by which we can calculate the Laplace transform of a given rational function. We use method of partial fractions to uh, reduce the given term into non functions. Now let's solve another one. Find out the inverse Laplace transform of s square minus 3s plus 8 divided by s cube. This is again a rational function, but we don't have to use any partial fraction techniques here. The method is comparatively simple method is available. We can split it into three fractions, like it is L inverse of s square by s cube is 1 by s minus 3 into s by s cube is 1 by s square plus 8 by s cube. Now, since Laplace transforms are inverse Laplace transforms are linear, it is L inverse of 1 by s minus 3 times L inverse of 1 by s square plus 8 times L inverse of 1 by s cube. Now, what we have is Laplace transform of t raised to n is equal to n factorial divided by s raised to n plus 1. And from here, this general expression, we can have L inverse of 1 by s raised to n is equal to t raised to n minus 1 divided by n here, t raised to n factorial divided by s raised to n. minus 1 factorial. So using this result, uh, we can have the Laplace transforms here. It is s raised to 1. So anyway, we know that 1 by s is the Laplace transform of 1. Then minus 3 times L inverse of 1 by s square. It is t Laplace transform of t is 1 factorial divided by s raised to minus 1. Okay, this is Laplace transform of t. Then plus a times 1 by s cube. So here n is equal to 3. So t raised to 2 divided by 2 factorial. Here we have 1 factorial and here we have 0 factorial, both are 1. So this is equal to 1 minus 3t plus 4t square. And to cross check it, if we calculate the Laplace transform of this thing, if we take the Laplace transform, it is the Laplace transform of 1 is 1 by t, 1 by s, minus 3 into 1 by s square plus 4 into this is 2 factorial divided by s raised to 2 plus 1. 2 factorial is 2, so it is 8 by s plus 1. So this is how we calculate Laplace transform for this particular case. So it's comparatively a simple case. Now let's consider another function. What about L inverse of 1 by s square plus 5? It's merely a simple one. Just um, so this can be written as 1 by s square plus 5 can be written as 1 by s square plus root 5 the whole square. So it is 1 by s square plus a square. So can be written as something like is equal to, if we multiply with root 5 and divide with root 5, what we have is the square plus root 5 the square. Now we can take the Laplace inverse because this particular function is non-function. So it is 1 by root 5 into L inverse of a by s square plus a square, which is the Laplace transform of sine at. It is root 5 into t. So this is a straightforward one. So this method can be used to find the Laplace transform of rational expressions like 1 by s square plus a square. And if you have something like L inverse of s by uh, s square plus 9, this is L inverse of s by s square plus 3 square. S by s square plus a square is the Laplace transform of cos uh, Laplace transform of cos at. So here a is equal to 3 and therefore here we have cos 3t. Okay, another simple. Now let's consider another function. Find the Laplace transform, inverse Laplace transform of 1 by 3s plus 2 divided by s square plus 9. the denominator is s square plus 9, uh, so that is something like a square plus s square. So we can rewrite it like this: L inverse of 3s divided by s square plus 3 square plus 2 by s square plus 3 square, which is equal to, the first case we take a 3 outside, and that is L inverse of s by s square plus 3 square, that is the Laplace transform of cos 3t, and plus this 2 is a constant taken outside. Then here what we need is 3 by s square plus 3 square, so that we can write it as the Laplace transform of sine 3t. For that we multiply with a 3 and divide with a 3, and what we get is this one. And since Laplace transforms are linear, we can write like this: is equal to 3 cos 3t plus 2 by 3 sine 3t. So the Laplace transform of the given function is calculated. And now we can have another problem. Find the Laplace transform of 3 by s minus 2 the all raised to 5. So here our process is like this. We know that Laplace inverse transform, Laplace inverse of 1 by s raised to 5 is known. It is equal to t raised to 4 t raised to 4 divided by 4 factorial. 4 factorial. Okay. Now we have the shifting theorem by which we know that if we multiply t raised to 4 by 4 factorial with the e raised to t, then the inverse the Laplace transform become 1 by s minus 2 the all raised to 5. So the inverse Laplace transform of this thing is e raised to 2 into t into t raised to 4 divided by 4 factorial. 4 factorial is 4 into 3 into 2. So that's the required inverse Laplace transform. And okay, here we have a 3. So we can make a one more step simplification. It is 8. So it is e raised to 2t into t raised to 4 all divided by 8. So that is our required Laplace transform. So that is how we use the shifting theorem to calculate the Laplace transform of functions. And now another one: find the inverse Laplace transform of L inverse of 5 by s square plus 3s plus 7. 5 by s square plus 3s plus 7. So first observe whether this one can be factorized. S square plus 3s plus 7, whether it can be factorized into simple linear factors or not. And obviously 7 is a prime number, so it has factors 7 and 1 only, and so the roots are not anyhow, they are not integers, so it's not simply factorizable polynomial expression s square plus 3s plus 7. So we try to express 5 by s square plus 3s plus 7 uh, as a perfect square. So this 5 divided by s square plus 3s plus we add the square of half of the coefficient of s. So 3 by 2 square minus 3 by 2 square plus 7, and this is equal to 5 divided by uh, s plus 3 by 2 the whole square, uh, then plus 7 minus 9 by 2. So this is equal to 5 divided by uh, s plus 3 by 2 the square, um, 7 minus 9 by 2, 7 into 2, 14, 14 minus 9, that is 5 plus 5 by 2. Now is something like the Laplace transform of sine at shifted by a parameter e raised to minus 3 by 2 dt, where this a is equal to root of 5 by 2 of 5 by 2. So we can write it in a required form, like is equal to 5 divided by s plus 3 by 2 the whole square plus root of 5 by 2 the square. Then here in the numerator we need a, so what we require there is root of 5 by 2. So here we multiply with root of 5 by 2 and divide the whole thing with the root of 5 by 2. So what we have is root of 2 by 5 into, here we have a 5, that 5 can be taken here, into root of 5 by 2 divided by s plus 3 by 2 the whole square plus root of 5 by 2 the whole square. Now this particular term is the Laplace inverse Laplace transform, or this is the Laplace transform of sine uh, root of 5 by 2 t, then shifted with minus 3 by 2 t. Then here we have a constant, and it is root 5 and root 5 it cancelled, so it is root 10. So this will be the required Laplace transform of function. Okay, there is a small mistake here. This particular term, the denominator is not 2, it is 4. So what we get here is 28 minus 9, this is 19. So this term is 19 divided by 4. Okay, so that will make a correction in almost all steps. So that is okay, we can make corrections. So it will come uh, root of 19 by 4, and here also we have root of 19 by 4, and what we multiply here is also root of 19 by 4, and that will make things different. So uh, here we get 19 by 4, and this is also root of 19 by 4. So in numerator we have 19 by 4. Here we have 19 by 4 square root of, and this term is also 19 by 1 by 19 by 4, that is 4 by 19. So what we get as the final answer, it is root of sine of uh, 19 by root of 19 by 4 t, and here this is root 2, root of 4 is 2 into 5, that is 10. So this is our answer. Okay, anyway, so this is how we calculate the inverse Laplace transform of that particular function. And now another one, let us find the inverse Laplace transform of s by s square plus 6x plus 25. S square plus 6x plus 25. The procedure is almost the same. So we make the denominator as a perfect square. For that, s square plus 6s. Then we add and subtract the square root of, sorry, the half of square of the half of the coefficient of s. That is, coefficient of s is 3. Sorry, 6. 6 by 2 is 3. 3 square is 9. So 9 is added and minus from the denominator. This is equal plus 25. Is equal to s divided by the first time become s plus 3 the whole square. Then what remains is minus 9 plus 25. Minus 9 plus 25 is 25 minus 9 is plus 16, and we have to find the inverse Laplace transform of this time. But what we have is the Laplace transform of cos at is s by s square plus a square. This is something like that. Instead of this a square, we have root of 16, that is 4. So it is cos 4t form, but this s is replaced with s plus 3, which means we have to use a shifting of this cos 4t with e raised minus 3t. So e raised to minus 3t into cos 4t, but still there is a problem. If in the numerator also we have an s, and that s is also have to be shifted with a parameter of 3. So for that we just rewrite it like this: s plus 3 minus 3, and this is equal to uh, s plus 3 divided by s plus 3 the whole square plus 16, then the remaining minus 3 by s plus 3 the whole square plus 16. Uh, this is equal to the first one, is simply e raised minus 3t into uh, cos 4t. The Laplace transform of cos 4t is s by s square plus 4 square, in which s is replaced with s minus minus t. Then minus here it is the inverse Laplace, the Laplace transform of sine 4t shifted, and therefore we need an a here. A is equal to square root of 16, that is 4. So we multiply and divide with 4. So 3 it is taken outside. Then we multiply with the 4 and divide with the 4. So we divide with 4 is here. Then the inverse Laplace transform is e raised to minus 3t into sine 4t, which is equal to e raised to minus 3t can be taken as a common factor, and what remains is cos 4t minus 3 by 4 sine 4t. And from here we can have a formula for the, say, what we have, base Laplace transform of uh, s by s plus a the whole square plus b square. Inverse transform of s by s plus a or s minus a the whole square plus b square can be uh, obtained in a single step as e raised to minus at into cos bt minus 3 by 4, that is a by b into sine bt, something like this. I think I tabulated the formula in our list of inverse Laplace transforms, and you can do method. Either you have to by heart the formula, or you can solve it for each and every independent problems. You can have one more problem, and let us consider find the inverse Laplace transform of L inverse of s plus 2 divided by s plus 1 the square, s plus 1 the square into s minus 2. So here uh, what we have to use is the partial fractions. So s plus 2 divided by s plus 1 the square into s minus 2 can be written as, using partial fractions, a by s minus 2 plus b by s plus 1 plus c by s plus 1 the square. Therefore this will give a into uh, s plus 1 the square by taking the LCM plus b into uh, s minus 2 into s plus 1 plus c into s minus 2 is equated to the numerator, that is s plus 2. Now we can substitute some values. First one, s is equal to minus 1. And s is equal to minus 1, it is 1 equal to, first time a becomes 0, this will also become 0, This is c into minus 1 minus 2, that is minus 3, which give c is equal to minus 1 by 3. And the next thing, we can substitute s is equal to 2. S is equal to 2, then 2 plus 2, that is 4, is equal to, here we get a 0, here also it is 0, so it is 2 plus 1 3, 3 is power 9, 9c, which implies 9a, which give a is equal to 4 by 9. Then to find the value of b, uh, to find the value of b, uh, there are many methods, but the simplest one, uh, the LHS and RHS are both sides are the same polynomial, so we can equate the coefficient of say s square. So here we don't have any s square. S square. Here we get. So what we are going to do is equating coefficients of s square on both sides. We have 0 is equal to, because in the left hand side there is no s terms of s square, so 0 is equal to. Here while expanding we have s square into a, then here when s into s plus b into b, so that's the term of b. A plus b is equal to 0, which means b equal to minus a, that is minus 4 by 9. So the given function become a by s minus 2, that is 4 by 9 by s minus 2 plus b by, it is minus 4 by 9 by 1 by s minus 1, 1 by s plus 1, then c is minus 1 by 3 by 1 by s minus 2, the s plus 1 the whole square, s plus 1 the whole square. So this is how we use partial fractions, plus 1 the whole square. Now we can have the inverse Laplace transform. So 4 by 9 into inverse Laplace transform of 1 by s minus 2 minus 4 by 9 into the inverse Laplace transform of 1 by s plus 1 minus 1 by 3 into the inverse Laplace transform of s plus 1, 1 by s plus 1 uh, the square. So taking inverse Laplace transforms on both sides, sorry, taking inverse Laplace transforms, we have 4 by 9 into e raised the 2 into t minus 4 by 9 into e raised the minus t minus 1 by 3 into, here it is what we have is 1 by s plus 1 the whole square, 1 by s plus 1 the whole square, and 1 by s plus 1 the whole square. So we have the Laplace transform of t raised dn is equal to n factorial divided by t s raised n plus 1, or in other words 1 by s square, 1 by s square is the 1 by s square is the Laplace transform of t. So t, Laplace transform of t is 1 by s square, and if it is shifted uh, with parameter e raised minus t, then its Laplace transform is 1 by s minus minus 1 whole square, that is s plus 1 whole square. So it is e raised minus t into t. So this is equal to, uh, we can simplify it uh, by taking an LCM, taking a common factor as 459 into e raised, 459 can be taken outside, and e raised to t minus e raised to minus t minus 1 t e raised to minus t divided by 3. So that's the required Laplace transform of the function. So this is some methods by which we can find the Laplace transform of uh, functions. And now we will uh, provide some more functions to uh, find the Laplace transforms. Just take it as a homework. 3s plus 2 divided by s minus 1 into s square plus 1 uh, using partial fractions. Then another one, find the inverse Laplace transform of 5s plus 3 5s plus 3 divided by s minus 1 into s squared plus 2s plus 5, again using partial fractions. And uh, find the Laplace transform of uh, say 3s plus 3s minus 2 divided by s square plus 2s plus 6. So just try to find out the inverse Laplace transforms of these three functions. And in our next class, we will uh, continue with a few more methods by which we can have the inverse Laplace transforms of expressions. So for the time being, we stop here.